Hi, and welcome to the next section in the tuning chapter, which is a rough overview on 3 more advanced tuning techniques. So we'll discuss very roughly and briefly the idea of evolutionary algorithms, the basic idea of Bayesian optimization, and of Hyperband as a multifidelity technique. So let's get started. So we've already covered grid search and random search as 2 really simple and naive techniques. So I guess we can call them optimization techniques, but they are definitely not very smart. So they are basically exploring the search space in a very unguided manner. So either by exploring a pre-constructed grid or by randomly sampling points, design points from the search space. They're really not learning or optimizing anything while that goes on. But this is, of course, exactly what we would like to do. Currently there are really a large number of different techniques that are being tried out for hyperparameter optimization. There are EAs, there's Bayesian optimization, and there's Hyperband. And these techniques can be characterized, for example, through how they handle this very fundamental exploration versus exploitation trade-off. So this is a very important trade-off that I guess every black box optimization algorithm has to get, well, I'm not sure whether I should say has to get right, but has to somehow deal with. The basic question is, if I want to spend some additional budget, for example, by exploring or evaluating, by evaluating a new point, should I rather look into the vicinity of something that I've already evaluated and that had good performance, so to try to kind of exploit that local information that I have already obtained, or should I rather use that budget to explore a region in my search space where I haven't explored before? Another distinction one could make, I guess we kind of came up with this a little bit ourselves in one paper. We call that, or at least the terminology, I guess, the fundamental ideas, of course, handled in many different algorithms in certain ways, is what we call the inference versus search trade-off. Do you actually want to spend extra computation time into learning as much as you can from prior evaluations as possible? So you will see this later on maybe we can go through the examples that we've already covered in the lectures before. So if we look at random search and grid search, they basically spend 0 computation time by intelligently figuring out where to evaluate next. And if you look at evolutionary algorithms, they do some form of computation. You will see how they compute the next points through mutation and crossover operators and so on. But these are quite cheap operations. And we are not kind of trying to squeeze as much information as we could out of the until now evaluated points. Bayesian optimization actually uses a machine learning model, quite often a quite expensive one, for example, a Gaussian process, in order to figure out where to evaluate next. And that comes with a certain amount of extra overhead. There are further aspects that are of interest, and we have absolutely no time here in this rough overview to cover them, but I just want to mention them briefly. So you should figure out how parallelizable your black box optimizer is. That's usually important if you want to create a more efficient optimizer and use your available hardware to full extent, whether they have more local or global search behavior, whether they can handle noisy observations, whether multifidelity approach is possible. Like I said, we'll cover one technique here very briefly under the name of Hyperband that can do that, and how they handle search space complexity. So, for example, mixed spaces of mixed parameters of numerical and categorical type, or even hierarchical search spaces. So let's start with evolutionary strategies. So in an evolutionary strategy, this is a class of stochastic population-based algorithms, which are inspired by the concept of biological evolution. So what we do there is we maintain a so-called population of candidates. This is just specific terminology for a set of candidates. So we don't have one single candidate that we locally improve over time, but we have a whole population of candidates. And this population is at the beginning is somehow initialized, and to keep things simple here, let's just assume we initialize them somehow randomly. And each of these candidates, they have a certain representation. For hyperparameter optimization, we'll simply assume that the representation is just a vector of values. So a vector that contains in the first component the lambda 1, second component the lambda 2, and so on. So all of the hyperparameters we're just configuring for our machine learning algorithm under consideration. And then we are usually also maintaining all of the objective values of these candidates. So these are denoted here with the C values. And in evolutionary strategy nomenclature, these are called fitness values. So what I'm now going to do is I'll perform one full evolution, one full generation of this population to hopefully improve this. And this usually works like this. So I'll usually perform some form of parent selection. So let me maybe come back to this a little bit later. So for now, we'll just somehow draw two parents. Let's maybe denote them here. So you have maybe a parent here and a parent here. And now I'm going to perform a specific operation on them, which is called the crossover operation. So this crossover operation would take a vector like this, and would take a vector like this, and combine them in such a manner so that a new vector is performed. So in one simple operation you could do is you could just, for example, randomly select the components of this child vector here uniformly from the parents. There are also some other forms of operations here. We basically cut here, and then you take, for example, this part and this part. But there's a lot of different ways of performing such a crossover. And then after we've done this, after we have created a new child here, so you can also see this here. Actually, maybe I should have explained this rather by using the available visualization here. You can see the parent. Let's maybe call this P1, and this is P2. You can see here the different values. You can see here the child, where in the first component we actually took that guy, and in the second component we took apparently also that guy from the first parent. And here we selected this guy, and here we selected that guy. And now mutation is usually a mild stochastic form of local perturbation to the child. So for example, what we could do is we could kind of flip a biased coin for each component, and then randomly perturb it a little bit depending on the outcome of that coin toss. So what we would see here is that all three of these guys, they are kept fixed, but this guy here, this guy is actually flipped and changed. After we have created a set of children from the parent population, so usually so one very well-known class of these algorithms is called mu plus lambda evolutionary algorithms, which work like that. So the lambda is now a little bit confusing because actually I'm using lambda for also to denote my hyperparameter vector here. So apologies for that. But these mu plus lambda evolutionary algorithms, what they do is that they maintain a population of size mu. Then they create. So this is, for example, here the population. This would be of size mu. And then they create lambda children. The children are also evaluated. This happens here in this step. And after I've done that, I would rank my mu plus, my new potential population of size mu plus lambda. And I'm going to filter it down again to mu values, but just taking the mu best in the ranking, killing off the lambda worst, and then I will iterate. And this is obviously a black box optimization technique. This can be nicely applied to black box problems that don't provide us with gradient information, as for example hyperparameter optimization problems. Usually the whole kind of the whole challenge in setting up a good evolutionary algorithm is getting these mutation and crossover operators right, and fiddling around with a lot of different control parameters. So of the evolutionary algorithm. So in a certain sense, you have to kind of meta configure those as well to a domain you want to apply them. But the nice thing is that they can handle basically any type of complicated search space. They can handle mixed spaces and hierarchical spaces, or even more complicated structures because you can create custom crossover and mutation operators for these. Okay, I guess I'm already spending too much time on this here and on this one slide. So let's move on to the basic idea of Bayesian optimization. So bear with me here. I will keep this really simple. I will also not mention any form of mixed search spaces and so on. So let's assume that our search space, our domain, is fully numerical for now. And that we have a black box function C of lambda. So lambda would be a numerical vector. I want to black box optimize this in a hopefully quite smart fashion. So the idea is, well, if the C function is unknown, but we are evaluating while we are optimizing a bunch of different design points on that C function, how about we try to learn as much of the C function as we can by the available points in our archive? So that does sound a little bit like a machine learning problem itself, right? So how about we use nonlinear regression to learn the mapping from lambda to the objective value? And then we can use that so-called surrogate function, so the approximation of that true C function here, to place a new point intelligently, evaluate that, then update our model and iterate. So this works in the following way. So assume that we have some points available, these guys here, and in our current archive. So we have their lambda values and we have their objective values in the archive. What we will now do is we'll learn a nonlinear regression function that maps a lambda vector to an objective value. For example, to the accuracy of our machine learning model on the data set at hand that we're currently looking at. And here in the plot, this learned model would be this bold black line here. And the true C function, which of course we don't know, because otherwise it wouldn't be really a black box problem, this is this dotted true function here. And of course, because we are doing this on rather small sample size data, because we will not be able to evaluate too many points, this approximation will not be super precise. Cannot really assume that this works perfectly. And now, after we have fitted that so-called surrogate model C hat here, we will now optimize that model instead of our true function, which is not available to us, in order to place a point. And one way we could do this is just like directly do what I just explained. So we take a look at the dotted function here, which is now cheap to evaluate, and we run some form of stochastic optimizer in this, for example, an evolutionary algorithm, or maybe even something that's gradient based, because maybe even gradients are available to us. And then we would take the best point from this dotted line here and evaluate that next. So that might be, for example, here. But you can already see that apparently this is only a part of the idea, because there's now something here in the lower part of the plot which is called an acquisition function. And this is kind of the one component of Bayesian optimization that I kind of left out until here. So we won't do exactly what I just explained. So we won't optimize the raw. Actually, I should have probably made a mistake. I should have. This is actually the true function. We would actually optimize this guy here. So maybe if we minimize, we place the point here. So, but we are not going to optimize this raw posterior mean of a nonlinear regression model. And the reason for this is somewhat subtle. to see if you haven't seen this before. So if we are doing that, what will usually happen is that we have a high probability of premature convergence where we would run into some local optimum, because if we are fitting this regression model to the archive points, and then there is like an area or some points which actually look quite nice, and then we have a large area where we were quite unlucky. We evaluated a bad point, but there's a super large unexplored area around this. We are really never going to place a point there, because our regression model will deem this area to be as or similarly bad as the bad points that we evaluated in that region. So what we have to do, and this is exactly this exploration versus this exploitation versus exploration trade-off, we have to somehow introduce that into the optimization process. And we're going to do that by forming something that's called a so-called acquisition function. And this works in the following way. So first of all, we're going to choose a certain class of probabilistic models for our nonlinear regression. So one form that works actually quite nicely with Bayesian optimization is called a Gaussian process. So we'll study this later, not in this lecture here, in this introductory course, but let me maybe summarize this in one or two sentences. So a Gaussian process is actually a very nice nonlinear regression model, which can work very well on small data, which is a local model. So it's kind of it's a kernel-based technique, so it's comparable to support vector machines, but it's a fully probabilistic model, which means we also get a nice uncertainty quantification, a so-called posterior variance or a posterior standard deviation for each point we evaluate. And this is, you've seen that actually before in the plot here. These were these shaded areas here, which were which are kind of located around this center of this posterior mean, so this bold black line. And what I've shown here in the plot through the shading is plus minus 1 standard deviation of the posterior uncertainty. And what the posterior uncertainty actually encodes is how, can say how sure the model is of its prediction at that particular point. And what the Gaussian process basically encodes in this posterior uncertainty is also how well explored the area around that point is. So if you take a look at direct observations, at direct design points where I have already, so points that are already in my archive that I've evaluated, the if you use an interpolating Gaussian process, the posterior uncertainty at that point will be exactly 0. Because we've evaluated that point, we know its value. And now the further you move away from that data point, and also other data points, the larger the uncertainty becomes. So if you move away from that point, the uncertainty grows and grows and grows and grows, and here it becomes smaller because we're actually getting closer to this second design point here, and then it goes down to 0 until we have exactly reached that point. Now, there are some nice ways of balancing out now this exploration and exploitation, which usually means we form an acquisition function, so we kind of form an extra function that combines the posterior mean, so the posterior mean of our regression model, which encodes the estimated objective value of our regression model at lambda, and the posterior uncertainty, which encodes the estimated uncertainty at that point, or we could also say how well we have explored the area around that point. And there are two well-known ways of combining them. So one is extremely simple. So one is the so-called lower confidence bound. So that takes the C hat function, so the posterior mean of the Gaussian process, and then does minus some control constant kappa, the posterior uncertainty. So what we're actually computing is, let's say kappa is 1, we would actually compute this lower bound here. So our posterior mean minus 1 time the posterior uncertainty. And that kind of can also see this as getting a bonus, an additive bonus to the posterior mean by through the uncertainty function. So the higher the posterior uncertainty is, the higher the bonus is. And then there's another alternative way, which is called the expected improvement. So I'll not really explain how that comes about, but what the expected improvement in a certain sense encodes as what is the expected move forward, or the expected progress you make, the expected improvement you make in optimization, if you evaluate at a point lambda, yeah, and if you kind of integrate out over the stochastic information encoded by your Gaussian process, and if you only handle, or if you assume that uncertainty in the Gaussian process or in the model only works in your favor. So I guess this is really not understandable here, and that in that very rough overview. But yeah, let me at least say that this expected improvement has some really nice theoretical properties. We can, for example, show that no point in the search space ever gets down to probability 0 of subsequently being explored, and we can actually show that this that Bayesian optimization combined with expected improvement, which is sometimes also called the ego algorithm, really behaves nicely as a global optimizer, and in a certain sense it never really gets stuck in local optima. Whether that means it's the most efficient black box optimization algorithm over a finite horizon, that's remains to be seen, or it does not directly follow from this. But at least it has some quite nice mathematical properties, and there's a very nice derivation of this expected improvement criterion here, and that for that reason many people like to combine this guy here with the Gaussian process for numerical expensive black box optimization problems. I guess I have a short animation here which we produced with our Bayesian optimization toolbox. So this looks, I guess, a little bit nicer than what we have seen before. So a few words of warnings about these univariate visualizations. They are, I think, nice for didactical purposes, but things become a lot more complicated in higher dimensional space. It's just much harder for me, or in a certain sense nearly impossible to visualize that nicely. So I'm showing this here with these super simple univariate functions, but don't get too much, I don't know, distracted by the simplicity of these animations and I don't know, patterns you see while the algorithm runs. So what you can see here is as a dotted line the underlying true function. As a bold line you can see the fitted model. As the red dots here you can see the design points that we have initialized, and this green guy here is the proposed point. When we are optimizing this acquisition function here, which is in this second lower plot, and you can see here this is apparently the expected improvement, and you can also see that the expected improvement, that's apparently quite a multimodal function. So using local optimizers for this surrogate acquisition function is probably not a good idea. We can also try to understand a little bit how the shape of that expected improvement comes about. So like I said, this is a combination of low posterior mean. So the lower this bold function here is, the better it is, and high posterior uncertainty. And we should be able to check that this point here, this has a somewhat low posterior mean. Actually, what's not so nice for this iteration here is that our Gaussian process estimates a nearly constant function. So I guess this will look a little bit nicer if we iterate a little bit. And then you can see here that the uncertainty is also quite high. The same here. It's a low point, but with high uncertainty. Again here, low point, but with high uncertainty. We would now globally optimize this guy here. So this A acquisition function, and at this global maximum of the expected improvement, we would place our new point, evaluate that now, really spend some budget to evaluate our expensive function C, and then iterate, adapt our surrogate model, maybe by just refitting it or doing something more intelligent. You have a kind of online learning on that new point, and then iterating. So you can now see here that we are actually model becomes a bit more precise. So it's still fitting pretty badly in this area here, but here it actually fits quite nicely. And this would now be the global optimum of our expected improvement. And this is where we would place a point there. And here you can now see that because we have explored the function also quite nicely, and we are pretty sure that we are capturing its shape, all of these uncertainty bands around the posterior mean, they become quite narrow, which means our expected improvement becomes quite small. Now, this point here doesn't have a very great posterior mean, but it has a quite high uncertainty band. And this is why we are now apparently exploring here. So our Gaussian process actually thinks that this point will be quite bad compared to this guy here. So that it will be worse. But it's not so sure about this, encoded through this large uncertainty band, and this is why the expected improvement is, as it combines the two, is still quite large. I guess that's it. So here's also a 2D animation where we are comparing now Bayesian optimization to random search. What am I optimizing here? So I'm actually tuning the complexity and minimal node size for a card tree on the Titanic data set. I'm using a 10-fold cross-validation, maximizing accuracy. What you can see here is this very uniform distribution of points for random search, and here you can also see a uniform distribution of Bayesian optimization for the initialization. But then we are actually exploring, or let's say exploiting rather, kind of precisely exploiting only this lower area here where this initial point was placed that had quite high accuracy. And you can see pretty nicely the difference between Bayesian optimization and random search here. Actually, this is not exactly sure what happens here. This is, don't want to call this degenerate, but usually Bayesian optimization would explore a bit more in between. So would place a few points also somewhere in between here and not kind of focus exactly on that one region. So I'm not sure, maybe this point here was pretty good in the beginning, or maybe we kind of configured Bayesian optimization here in a certain way so that it put more weight on actually exploiting the function instead of exploring. Last algorithm is very, very simple one, but nonetheless has become quite popular. So this is called Hyperband, and the underlying principle is called multifidelity optimization. So what we will now assume is that there's one special hyperparameter in our search space, and this special hyperparameter we will call the fidelity hyperparameter, or lambda fit. So this is a component of lambda that influences the computational cost of the fitting procedure in a monotonically increasing manner. And usually the idea is that, I guess let's assume that lambda fit actually goes from 0 to 1. And let's maybe take two very common and interesting examples, so you already have something in the back of your mind and it's not so abstract anymore. So one thing, so the first example would be you are, for example, optimizing a neural network, and usually a neural network is optimized in epochs. So you have a number of epochs, number of iterations until you have fully optimized your neural network. And of course, they're usually not going from 0 to 1. So let's assume this is somehow rescaled. So 0 is doing no epochs and 1 is doing 100% of all of the epochs. I don't know, maybe you're doing 500. So the 1 would be equal to these 500 epochs. What we can now do is we can optimize for 10 epochs, 100 epochs, 200 epochs, or 500 epochs. And the less we use, the faster our training procedure will run. But of course, the less we usually have fitted our neural network. Because we have actually only spent a fraction of the budget we deem, necessary for training the thing. Another model agnostic way of making any machine learning algorithm accessible to multifidelity is subsampling the training data. So in this case, the multifidelity parameter from 0 to 1 would equal the percentage of training data we are using for training. So we're not going to use everything for training, but we're actually using less. So for example, only 10%, 20%, 50%, or 80% of the training data. And the reason is, the less training data we use, of course, the faster our training procedure will run. Of course, again, the less well we will fit our training data. And methods of multi-fidelity optimization in HPO are now tuning approaches that can somehow efficiently handle such a multi-fidelity structure. And how we are going to do that? So the basic idea is to evaluate things with a low budget, then take a look at the estimated or approximate objective value we get from that, and then kill off stuff early that does not look very good. And we can do that in Hyperband through a very, very simple procedure. So Hyperband can kind of explain that as an iterated form of successive halving, or you can also compare this to random search. So let's exactly explain these two components. So let's start with successive halving. So successive halving assumes that there's a set of candidates, and the only thing that you want to do is you want to drill down or filter down the set of candidates to the best performing candidate in a very efficient manner. So without evaluating everything with full budget, because that would kind of be the naive approach. I guess you spend a full evaluation on each candidate and then you just, sort them, take the best, and you're done. And the idea here is to do this hopefully a bit more efficiently. Yeah? So let's assume we have 8 of these candidates, and you can see them here as these colored lines. And on the x-axis here, we have our budget parameter. Also, actually, this is I guess a little typo here. So I guess I called that the fidelity parameter before. So I guess that should be lambda fit. So we have our fidelity parameter here on the x-axis. And what we are now going to do is we're going to evaluate all 8 of these candidates in our set with 12%, actually I guess 12.5% of the available budget. And then we're going to rank them, and we're going to kill off the worst 50% of these. So these guys here, these will all be killed off, yeah? And these guys here, they will remain. And this is also why these guys here, they begin to only have shaded lines. So these shaded lines are how their objective value would develop if we would evaluate them in the future, which we're not doing because we have killed them off. And now what we're doing is we are doubling the budget to 25%, doubling the value of fidelity parameter, I should probably rather say. And then again, killing off the worst half, only sticking with these 2 guys here, doubling the budget again, then killing off that guy and having that evaluated with 100%. And you can see here that in this case we were lucky. We actually, with much less budget, figured out which was the best performing configuration among these 8. Of course, you can see that you can actually go wrong if you're unlucky, right? Because these evaluations here on these lower fidelity levels, they are not super precise. They are not perfect. And if you're unlucky, these lines here later on can cross, which means you're actually killing off the wrong candidates potentially in earlier stages. But assuming you do this roughly correctly, you are saving all of that budget here, which you would have spent otherwise by fully evaluating everything, and you can now use that budget to do something else. And what we are doing in Hyperband is that we are now iterating that procedure here and running a couple of these successive halving races, or some people also call them brackets. So the basic insight is, or the basic challenge is, how should we kind of, this is kind of, you can call it, I guess, a schedule, kind of a setup for successive halving. How should we do this? Yeah. So how many configurations should we initialize our successive halving run with, and when should we evaluate? And it seems to be pretty obvious that if we use more configurations in the beginning, we can explore our search space better. And also if we evaluate these guys too early, we have an increased probability of killing off the wrong guys. So Unfortunately, we can't really have these two things together, have lots of configurations and evaluate them very, very late in the process, because combining these two things together would create a super expensive schedule. So what Hyperband actually does is it tries out different schedules, with different trade-offs. So for example here, we have this bracket 3, and bracket 3 starts with 82 candidates in the beginning, but evaluates them only for 1 unit of the fidelity parameter. And here we have also this eta parameter, and eta tells us how we should, through which factor we should filter down our candidates. So this is here, in my example before, I used an eta of 2. So I divided, or I reduced my candidate set to the best 50%. So if eta is 4, I'm reducing to actually 25%, to 1/4 of the available candidates. But I will also multiply my fidelity parameter now by a factor of 4. So here is a multiplication with 4, and here's a division of 4. And now we are drilling down these 82 to 20, and then to 5 and to 1. And here you can see different brackets with different initializations for this fidelity parameter and for this initial number of candidates. So here I'm starting with 27, but I'm having them run 4 fidelity units. Or here in this last bracket, I'm actually starting with 5, but I'm having them run for the full horizon of the fidelity parameter, which apparently here goes from 0 to 64. And all of these candidates here, they are initialized randomly. So in a certain sense, this is, I don't know, some iterated form of random search, where in each kind of random search iteration, you are kind of drilling down your set of randomly uniformly generated candidates through successive halving. So I guess this video became a little bit longer than I wanted it to be, but I hope it was somehow helpful to understand the basic ideas of these more advanced algorithms. Of course, there's a lot of other stuff that we couldn't cover here. So there's, for example, different stochastic local search algorithms. You can use some form of simulated annealing. There are more complicated genetic algorithms or evolutionary strategies. One pretty well-performing one is, for example, covariance matrix adaptation. There's iterated F-racing and lots of other stuff. If you're interested in this topic and also the mathematical formalization of hyperparameter optimization, have a look at our paper. This is freely available on arXiv, and this is a lot longer than what I covered here.